Here we want to investigate the other computation used with vectors known as the cross product or vector product. And the definition of the cross product, you see that we have still some things that are being multiplied, hence the use of the word product. Only the pattern for multiplying these is a little difficult to catch on to and use. So I'll show you some computations that are used for doing cross products. These are also called vector products because the result comes out to be a vector, whereas the dot product comes out to be just a number. And the cross product is only valid for 3 dimensions. Now, one of the reasons is that the cross product of two vectors, the vector that results from that, is perpendicular to both of them. Well, the vectors u and v would define a plane, and so a vector that is perpendicular to those would have to be coming out of the plane. Therefore, it would have to be 3-dimensional. Now, here's a graphic to help you see what the cross product does. I've graphed in Maple the two vectors u and v, blue and green respectively. We're going to do the cross product of u cross v. Now, to do u cross v, using the right hand rule, you'd point your fingers of your right hand along the blue vector with your fingers curling towards the green vector. And then your thumb would point in the direction of the cross product. For these two vectors, here would be the u cross v, and here would be the v cross u. We'll look at 3 methods for computing cross products. This first method, known as Sarris rule, you write a determinant with the ij's and k's along the first row. This vector has to be the first vector of the cross product, and this vector has to be the second vector of the cross product. They must be in that order because the cross product is not commutative. Sarris rule goes like this. We duplicate the first 2 columns on the right side of the determinant. Then we join diagonals in this direction. The product here of the I and the U2 and the V3, the product of the J, U3, and V1, just follow the green lines, and then the product of the K, U1, and V2. Then, in the opposite direction, we will do these products, but they will all be negative. Now, if you put the I's together, the J's together, and the K's, you'll see we come out with the formula for the cross product. And here's another method that does the same thing with the technique of expansion by cofactors. Again, I've written the determinant with I, J, and K along the top row, first vector underneath, and then the very bottom is the second vector. Now, expansion by cofactors, you can take any row or column. We'll start with just the top row. Take each component, and the signs would be positive, negative, and positive. I can't go into all the details about how to get the right signs on this if you expand by other places, but I can show you that in class sometime. However, the technique goes like this. If we cross out the row and the column where the I is, the components that are left would be the determinant that we need to evaluate now. And the same thing for the J. Cross out its row and column. And for the K, cross out its row and column. Now, the method of evaluating the determinants 2 by 2 are to multiply, multiply, and subtract. Multiply, multiply, subtract, multiply, multiply, subtract. And this is the same formula that we had before. I'll bet you can guess the third method for finding cross products. It is indeed type it into the TI-89 calculator. There is built into the TI-89 the CROSSP, cross product. You can get that from the catalog, or you can literally type CROSSP. So I'll demonstrate the use of each of these techniques. First off, Sarris rule, we write the IJK across the top, the first vector of our cross product. Let me point out here, that's what we're trying to do, and our first vector is U, so the negative 2, 3, 1 comes first. And then, of course, our technique was go this direction, all positives. I times 3 times negative 2 is negative 6i. J times 1 times 4 is 4j. K times negative 2 times 0 is 0. When we go the opposite direction, we make them negative. So this first one is K times 3 times 4, which is 12K, but we want the negative of that. And then I times 1 times 0, well, you can't go wrong, whether it's positive or negative, on 0. J times negative 2 times negative 2 is 4j, but again, we want the opposite of that. And then we just simply combine like terms, and we can write that in our component form if necessary. The cross product of the same two vectors using the Laplace method. So again, we write the A, J, and K as the top row, first vector, and then second vector. Then we want to cross out the row and column for the I, take the remaining 2 by 2 determinant, then cross out the row and column for the J, take the remaining 2 by 2 determinant, and of course the J, if you're doing this, is going to have a minus on it. And then the last one, the K, cross out its row and column, and write down the 2 by 2 determinant. When you evaluate the 2 by 2 determinants, you'll start by multiplying these two together, multiplying these two together, and subtracting. Now again, get to where we could just do that sort of in our heads. This first one is 3 times negative 2, which is negative 6, 1 times 0, which is 0, and negative 6 minus 0 is just negative 6. On the second one, we have negative 2 times negative 2, which is 4, and 4 times 1, which is 4, with a minus in between. And likewise, you can see on the third one. And again, simplifying that, we get the same answer. On our calculator, we can do this several different ways. But here, we've taken the u vector and stored it as the variable u. We've taken the v vector and stored it as the variable v. And then we've done the CROSSP. Now this has to be U first and V second. So the properties of the cross product have some of the same characteristics as the properties of the dot product. Except, of course, the commutative property, which you don't have such a thing for cross product. You do, however, have the relationship that the cross product is equal to the negative of the cross product if you reverse the order. And this is very similar to the distributive property that we used back in beginning algebra. If you just replace the cross with the times sign, you would have what we normally think of as the distributive property. The thing to remember about this is, of course, that the order is important. You can't go swapping the u's and the v's around. Very similarly, this is like the associative property, where you can put the constant with the u vector or the constant with the v vector. And here's an interesting one, very similar. Remember, in the dot product, if you dot a vector with itself, you get the square of the magnitude. Well, here, if you cross a vector with itself, you get what's known as the zero vector, which is actually an infinite number of perpendicular vectors. This has an interesting relationship. It's referred to as the triple scalar product because the answer comes out to be a scalar or just a number. And again, we'll see how to do that calculation in just a minute. Finally, the last one is very similar to the relationship that we saw with the dot product, where we had the magnitude of each vector multiplied, and this time we've got the sine of the angle between them, and that comes out to be the magnitude of the cross product of u and v. Now here's a method for computing that triple scalar product, which you'll see in the homework. What are some of the things you can do with the triple scalar product? And so, to do a triple scalar product, we simply take the three vectors in the order that we have them listed here, put them into a determinant, and evaluate the determinant. Now, since we've already done the evaluation of a 3 by 3 determinant, I'll kind of go through this quickly. We'll expand by the top row. We'll write down the 2, 3, and -4. And the middle one, the 3, needs to be negative. The other two, positive. Well, the 4 already was negative, so it's a positive -4. However, when you cross out the row and the column and write down the determinant that remains and then multiply, multiply, subtract, here's what we would get, which comes out to be a 58. Now, another way of doing the triple scalar product is to have a program on our calculator that does the triple scalar product. I've created one called TSP. You can probably figure out what TSP stands for. And this could be used to do a triple scalar product. So here are three applications using cross products. In this first one, we're finding the area of a parallelogram. Now, what that means is, if you have two vectors, here's the vector v and the vector u. If you start from the tip of v and draw a vector exactly like u, but from the tip of v, likewise, from the tip of v, we have this vector, which is exactly the same as vector v. That forms a parallelogram. The area of this parallelogram is nothing more than the magnitude of the cross product of u and v. Now, it doesn't matter which way you cross those two, because you'll get opposite signs, same direction, and when you do the magnitude of it, it's going to wipe out the signs anyway. So, to find the area of a parallelogram, we simply need to do the magnitude of the cross product. Now, we could also do this, which we saw was the same thing as the magnitude of the cross product. If we have three vectors, and we draw vectors here that is parallel to v, and one here that is parallel to U, and then this last one out here that is parallel to W, then we have what's called a parallelopiped. We can find the volume of that three-dimensional figure using the triple scalar product, U dot V cross W. Now, this could come out positive or negative, so we will be doing the absolute value since we don't care whether it's positive or negative. Volume will always be positive. And this final one is a physics topic called torque. Torque is a measure of the tendency to rotate. You see here they've got this, which is a fulcrum that we're rotating this thing about. So we're going to be pushing on here in this direction, the F that they're calling it. So we're putting a force on that. Hence, it's going to be twisting this object in this direction. And so the torque measures like what the force is. If it were removing a bolt from a machine or something, that's how much pressure we're going to need to put on it. So we can measure the torque by doing the cross product of R and F, where F is the force that we're putting on the object, and R is called the radius, the distance from the center to where we are applying our force. That's the R. And then the F is whichever direction we're applying our force. I'll let you figure out, if you understand this statement or not, where are we going to get our maximum torque? How can we optimize our use of our wrench in removing that bolt? I'll give you a clue. Look at this. What angle should theta be so that sine of theta has the largest value possible? And I won't tell you that, but I'll let you investigate it.